Hello everyone. Believe we are still waiting for everyone else to join. No problem. Meanwhile, let me share my screen. Hi Rohi. I hope you can hear me, right? Hello.
Hello. Yes, yes, I can hear you.
Okay. Let's wait for 1 minute. See if Saransh is going to join. Else, let's make a start. Uh, Let me just see. Yeah. Okay. I see Saransh has joined in as well. So let's make it a start. Okay. So until last week, what we have seen is we have seen some basic visualizations. We looked into joint plots, and then we also looked into this problem statement of how to come down from the top of the mountain to the bottom. Now we wanted to start with inferential statistics because of lack of time we couldn't start. So let's do it now. So what we are going to do as part of inferential statistics is we are going to primarily look into testing our hypothesis. So what I mean by that is that we are going to look into scenarios using existing data, which is the iris data set that we have, and using, let's say, dummy data or using some other data sets which we are going to use in the course of actions now. And we are going to look at one test right now. Okay, so we are going to look at one kind of test that we have already seen earlier in Excel, basis which we could do a comparison, or we could do the finding of the z critical value and the p value. Okay, so just to make our lives simple, and because of that I've already told you that we in the industry, right, we prefer p value over z values, and that is why we are not going to do z tests. Now p value can be found out using p tests, even from z tests, and then there is a very common test that we perform in statistics which is known as the t-test. Using this t-test is where it is the most common or most frequent way of actually getting the value. Okay, so the value for p, or the probability value, is something that we are going to get. Now I just want to quickly revise what we have already seen earlier, and that's why this first cell is going to come handy. We're going to keep that as it is. We're not going to use or we may want to use that variable alpha, but the reason why we have defined alpha is because that is the acceptance level, or it is also known as the significance value. Okay, this is the significance value, otherwise in the significance limit. There are a lot of things that it can be called as, but what is entirely refers to is that if you remember those days when we have already looked into, let's say, the empirical rule, right? So let's just quickly draw one small thing and try to quickly revise. This is my normal distribution, and it is if it is really a normal distribution with sample size or trial size more than 30, then what I know for sure is that as I go beyond that value of 30, my distribution becomes normal and normal and normal, as closer to normal as possible, which gives me the ideology to use central limit theorem. And central limit theorem comes hand in hand with the empirical rule, where the empirical rule says that if this is the mean value, which is the peak, right? So this value over here is the mean. If this is the mean, then I clearly have some more values here as well. Let me quickly draw those lines and quickly revise what we are going to see, because then only we'll understand the programming. Otherwise, we won't. Okay, if we want to understand the value of the program, then we need to understand this. So this is -1 sigma, this is +1 sigma, right? We have already seen this. So I'm not drawing the rest too. So this is 1 sigma range. Okay, this is 2 sigma range, and this is 3 sigma range, right? So within 1 sigma, how much falls? On this side I have 34%, this side I have 34%. Okay, so 68% of the values fall within mu plus minus 1 sigma. Then what is the 2 sigma? 95%, right? What is 3 sigma? 99.7%, right? So 3 sigma becomes 99.7. So clearly there is not much difference between 95 and 99.7, right? Hardly 4.7% of difference. Okay, but if you look at the difference between 68% and 95%, there's a huge hop, right? Huge jump. And so that is the reason why. And then in various different cases, we have also observed practically that if I have the average value of some kind of a distribution or a set of random variables, then I clearly know that mu plus minus 2 standard deviation covers 95% of all of the data. This is quite good a benchmark for me, and that is the reason why this 95% becomes the confidence interval market standard. Okay, just wanted to clarify this because there should not be any doubt as to why we are choosing 95%. Okay, we're not choosing 95% out of random. There is a logic behind it. There is no way to mathematically prove this. You will need a lot of maths to prove this. I mean, there is no easy way, I would rather say, to mathematically prove this, but you can prove this. Okay, so if you get any data set, you can try and prove this. Okay, try and find out the mean of the data, try and find out the standard deviation of the data, then you try and verify. Let's say you have an Excel sheet with 100 rows. Okay, try and verify if in the second column where you have 100 values, try and see if 95% or most of the data is already covered under sigma plus minus 2 or the mu plus minus 2 sigma, right? You will see that many of the cases that value will go beyond 95% as well. Just a minute, let me just come back. Yeah. Okay, so that is the reason why we are using confidence interval equal to 95%, and that's why alpha becomes 0.05, because alpha being the significance value or significance limit or significance level is 1 minus Ci, Ci represented in the probabilistic value, hence it is 1 minus 0.95, hence it is equal to 0.05. Why I'm stating on this value? Now you remember what we have done in the tests that we have done wherever we have used p-value, right? Wherever we have used p-value, very simple ideology. If p-value is less than alpha, okay, the value of p is less than alpha, we reject the null hypothesis. This is the aim in life for us, right? Our aim is to prove that our alternate hypothesis is the correct hypothesis. Null hypothesis was always wrong. Status quo has to be proven wrong. That is why we are finding out the p-value. We are going to do some tests now to find p-value. I'm going to take some dummy examples. Okay, completely dummy. I have 3 to 4 examples to take. They are completely dummy basis this iris data set only. But I will tell you what is the industry relevance using the examples from time to time. Okay, so don't worry. Now, clear cut, p-value less than alpha, less than equal to is not the criteria. Less than alpha. Okay, you have to be very specific. Okay, if p-value is less than alpha, then we clearly say I am going ahead and rejecting the null hypothesis. Okay, if I do such tests and find the p-value, then I can be sure if my null hypothesis was right or alternate hypothesis was right. Okay, now specifically to do this p-value finding, I'm going to make use of a test which is known as t-test. Okay, we have not in detail looked into t-test. We briefly touched t-test. We just looked into t-test as a singular line kind of a thing. One day, if you remember, we opened a Wikipedia page and we looked into it. Right, so let me first quickly describe what is t-test, because this is one of those topics which I did not cover deliberately during text or the theory sessions, because you wouldn't have understood what I'm trying to do. Now that we are going to do practically, you will understand far better. So what we are going to do in t-test, also known as a student's t-test. Okay, why is this called student t-test? As a very interesting story behind it. You can go to Wikipedia, search for t-test, and you will find the story there. The person or the scientist or the professor who found out or devised the mathematical foundation of t-test used to go by the name student. Okay, he gave him a name student. It is just like a name which we also give ourselves when we go on to online gaming platforms and we give ourselves a dummy name, right? So he gave himself a name student. That is why this rule, this application or this math become famous as student t-test. Okay, now student t-test clearly is used for two scenarios. Okay, I can have two scenarios in which I can use student t-test. Scenario number one, when I want to compare a sample and a population. Okay, why do I want to compare a sample and a population? Let's look into this, then we'll go on to point number two. Why we want to compare sample and a population is because let's say you have a humongous data set in some kind of a database. Okay, and Sarangs, let's say, is working as the data engineer in the database, or he is the DBA. Now you ask him to give yourself a representative sample. Because of some reason you don't have access to the data, because of some reason you don't know how to extract the data, whatsoever the reason might be, you have reached out to Sarangs and you have asked him, boss, I need a sample of the data. When you say sample of the data, irrespective of what he has understood from this statement, what you actually mean is that sample, that subsection that you select out of the population should be a representation of the population. It should have all the variety captured as you see in the population itself. So that is the reason why you are asking for a sample. Okay, that is the main motto of you asking for a sample. Somehow he has given you a sample. Before you start with the analysis, it is your duty, it is your aesthetic duty, ethical duty to ensure that whether or not your sample is actually a representation of the population or not. How do you do that? You compare the means. As simple as that. You take the random variables and you compare the mean. You do a probabilistic test. In this case, we are going to do a t-test to find out what is the difference between the statistical measures or the descriptive statistics measures of the sample and the population, the most important one being mean. If the mean of the sample closely represents mean of the population, I can say that it is going to represent the sample is going to be a representative of the population to a good extent, right? But I cannot stop there. I have to verify the standard deviation as well. Why? Let's say the population is a normal distribution, then the sample being a representation of the population in the right sense, sample will also be a normal distribution. The standard normal distribution says what mu is equal to 0, sigma is equal to 1. That's the sampling distribution representation of any distribution of random variables which is normal in nature, which means this rule of CLT, rule of empirical rule, and so on, is also going to apply equivocally on the sample as it applies on the population, right? That's what you need to verify. You cannot blindly trust the data that Sarangs has already given you, right? He may have done a mistake. So that's why you have to verify this. To verify this, with you a t-test where we are going to compare a sample with a population. Okay, if I'm going to compare in this scenario one sample with a one population or a sample that is part of a population, this test is otherwise known as a one sample test. Why am I saying this a one sample test? Because in this test I have only one sample. As simple as that, right? As the name suggests here, I have only one sample. I'm going to compare that sample within the population from where it is taken, and so on. The only data you need, only thing you need is out of experience or out of domain knowledge or out of the domain expert who is going to give you this information, unless you are one, is the mean or the average of the population. That's all you need. If you have the mean of the population, you pass it on to a function that we are going to see right now from the SciPy library. We have already imported it. There's a stats module in the SciPy library. We're going to make use of that and find out what is the difference between mean, median, mode, standard deviation, variance, and so on and so forth. All the statistical measures of one will be compared with other, primarily the mean and the standard deviation, to come to a conclusion whether this sample is a representation of population or not. And the only input it needs is the set of this sample and the mean of the population. You give that as an input to a function, it gives you the p-value. As simple as it sounds. Okay. The second one is where you are going to compare a sample with a sample, or a population with a population. This is a really interesting use case. Why am I going to do that at the first place? Okay. The reason why I compare a sample with a sample is because let's say there is an experimentation going on. And within that experimental study, I am giving you a sample. Sarangs is giving you a sample. Okay. I have one sample. Let's say Rohi has another sample. Okay, so if we both have two samples, one from me, one from Rohi, Saransh wants to verify whether those two samples are somehow related to each other or not. What it means by that is if they belong to the same population and they are really representation of the same population, which means both are equally good samples of the same population from where they are drawn, it is quite clear that they will have common characteristics, right? It is very easy to understand. If I have taken sample of, let's say, if I have sampled people in the housing society where I'm staying and I have taken their heights, and Rohi has also taken the same thing. If our sampling is really at the grassroots level, then the details, the attributes of my sample will very closely represent that of his sample, and that is both of these samples are also going to represent the population. But in this case, what I'm going to do, I'm not going to be bothered about the population. I'm going to take these two samples, try to do some statistical tests and find out what is going to be the p-value. Okay, what is going to be the chance that these two samples are actually very closely matching with each other. Okay, same happens when I'm trying to compare a population with a population. Why do I want to compare a population with a population? Let's say I am part of an organization where I am actually launching products every 3 months, every 6 months. Okay, if I'm going to launch a product now, I need to verify whether my customer base is going to respond to the product equivocally as they did in the last 6 months. So let's say this is what, July, right? So let's say I have launched my first, or the first product of 2020 was launched in the year January, right? Now I'm going to make another launch in the month of, let's say, July. So there is already 6 months of duration which has passed. I want to know whether the population or the characteristics of the population to whom I'm targeting this. Now this is no longer a question of a sample. Right now, this is a question of whether or not I'm going to make a launch, and then that launch is going to really affect all of my customers. It may well be a product launch, it may be a change in the UI, it may well be as simple as a simple change which Facebook or uh, Google is trying to implement in their website. Right? It can be as simple as that. It can be as big as a new product launch. Let's say GeoMeet. If GeoMeet was launched at this point in time, I hope you have heard, GeoMeet has been launched as a free product right now. It gives you the capability of what we are using this Zoom meeting for free. Okay, I'm not sure whether it provides the recording kind of a capability right now. Maybe some features are missing from there, but the service itself is free. You can use it as much as you want. You don't have to pay even a single rupee. Okay, now the point is, let's say 1 year back Geo had the last product which it has launched. Let's say that was Geo TV or maybe Geo Music or something else. Geo wants to know whether I'm going to make a launch of this Geo Meet and whether my population is going to be attracted towards the new product or not. In this case, they are not going to be considered about a sample. They don't want to know whether people in Pune are going to be interested or whether in Ahmedabad people will like the product or not. This is about India. They are going to make a launch over India, right? So they want to know what is going to be the impact of the product launch, if that is going to be taken seriously or that is going to be a lucrative offer for my population or no. In this case, they would like to compare the first or the earlier statistics of the population with the current statistics of the same population. In some cases it can be same, in some cases it can be different. The example I took is where the population remains the same. Earlier also the population was Indian population, now also the population is India's population. I'm trying to compare population of India versus population of India. It may well be the case that I'm trying to launch a product in the US when I've already launched the product into Philippines. And I would like to know whether my launch into Philippines is anywhere related to that which I'm going to do in the US or not, in the sense that whether people are going to like that or not. If that's what I'm going to do, then I have to compare population by population, and that is when I'm going to make use of t-test, when I'm going to compare two populations. Okay, there are a lot more examples, some of which we are going to take using the dummy data set which we have, and then we are going to answer those kind of questions. Okay, so let's start with the basics and then we'll go ahead. Now, at least until this point in time, if anyone has any questions, please let me know, because now I'm going to code.
From me.
Okay, okay, fine. Okay, now the first question or the first thing that I'm going to do is that I would like to find out if a sample that I'm going to take, or I may have already taken, is that really a representation of the population. That is the mean of the sample same as the mean of the population, or the characteristic of the sample is the same as that of the uh, of a population. So the first test that I'm going to do, first test, okay, this is where I compare the mean of sample and mean of population. Okay, in this case, I consider, okay, the let's say, how can I say, uh, uh, I consider Setosa species. Okay, just to make my life easy, I'm going to consider Setosa species, or I'm going to consider all species. I consider all species of iris flower. All species is not going to be a sample, right? Because then that becomes a population. No, let me select a species. I consider only Setosa. Okay, let's say Setosa species of iris flowers. And here what I'm going to do is that here I take a sample of 10 values out of 50 values. Right, so we have 50, 50, 50 values for each and every species, right? So there is 50 values for Setosa. I take 10 values out of those 50 values, considering only the petal length. Okay, just an example. I'm only considering the petal length. Now, why I'm considering only the petal length? A very important feature, you can consider at one point in time only one feature or only one column. Why? Because that one column represents one random variable. You cannot do any kind of statistical tests on multiple random variables on one axis. So what I mean by that is, t-test can be of two types, right? Sample to population, population to population, sample to sample. Now the last two that I said are part of one single group. Okay, I'm trying to compare sample to population or sample to sample, population to population. That is two sample test, right? Even in case of one sample test, the variables that I have used is a sample and a population. So x and y is there, right? So these I will call the axes. Now in these axes, you can have a series of data and not a data frame of data, if you know what I mean. In Python language, I can only use, just to give you a good anagram or some kind of an analogy to relate back to, you can only use one column or one feature of data. Why? Because you need to use the statistical measure not of the data but of a random variable, and one random variable is actually represented by single column. That's what you are taking, right? So that's why I have written here, I take a sample of 10 values out of 50 values total, considering only petal. Okay, now um, I would like to test if the mean of the sample and the mean of the population match, which means my null hypothesis is sample is a representation of population, right? So my clear cut uh, status quo is that the sampling that I've done is great, right? So the sampling is perfect. What is going to be the alternate hypothesis? Simply a copy paste. Sample is not a good representation of the population, right? So this is the first test that I'm going to do. Okay, now you might be wondering, in a data set of this size, if I'm only going to compare the mean, I can simply compare the mean and I can come to a conclusion. You can't do that. You have to compare the mean, the standard deviation, and all the totality at one place, and there is a formula, there is a mathematical representation to do it. You would like to solve that using NumPy, please go ahead. There is no problem, because NumPy itself is background coded into C, right? So it's quite fast. But there is, or there are already libraries provided by Python. That's what we are going to use, right? So what we are going to do first of all is that I am doing, this is a one sample t-test. Hence the inputs are, what are the inputs? First, I need the sample values. Okay, then I need the mean of population. Okay, or the population mean, right? Outcome will be calculate the p-value. Okay, and then basis the p-value, ascertain if we accept or reject the null hypothesis. Let me do one thing first. I'm feeling very awkward like this. Let me just Yeah, this looks good. Okay, now I'm just going to execute this, and now I'm going to first of all do some kind of a functional programming. Let's say I define a reusable function to calculate if p-value is less than alpha or not. So I create def check p-value. Okay, and I pass the p-value as the input. Somebody is going to pass the value. Compare with alpha if less than alpha, say we reject null hypothesis, else no, else not. Okay, so what I simply say, if p-value is less than alpha. Okay, alpha is already a global variable, so this code should work. Alpha is already created over here. If p-value is less than alpha, I simply say I print we reject, okay, reject null hypothesis. Okay, and else what we do, we simply print this. We failed to reject our null hypothesis. This is just a function that I've created so that I can reuse it. Right now, what I'm going to do, I'm going to take simply a sample, right, of the data. So in this case, I want to consider what the setosa flower. Okay, so taking a sample of the petal length for setosa flower. Okay, I don't have to do much calculations. You know why? Because I already have this iris setosa. I already have a data frame like this which belongs to setosa, right? If you remember, species equal to 0 belongs to setosa. I've already created this, so I'll use this, and from here I would like to choose the petal length. Right, so these are the values of the petal length. So I need these values so that I can create a sample. So for example, this list of value is what? This list of value will be 50. I just need 10 values out of it. Okay, so how do I do that? I just need 10 values out of it. Okay, there is a very simple way of doing it. Okay, iris setosa petal length is of type, sorry, oh sorry, I think this is fine. I by mistake clicked uh, on the insert key. Okay, so iris setosa petal length being a series, in Python, I have a function, okay, which is known as sample. So I simply call the function called sample, and I pass the number of samples that I want. Okay, in this case, let's say I'm saying n equal to 10. Then there is a very important feature. Later on, when we do machine learning, we are going to use this feature again and again and again. Especially when I'm going to share my research with you and you are going to share your findings with me. It is known as a random state. Okay, what is this random state? This is like, you can say, a bit or a pinpoint or kind of the strategy or kind of the methodology. The way you have created the sample, if you fix the random state to a certain value, you can give any value, any number. Okay, let's say I give a value of 1. If I give a value of 1 and I just execute this statement again and again and again and again, again and again and again and again, you can see it is actually picking the same sample. Are you getting the results here? See, this is the 80-second execution. The list is same. You see, it starts with 1.5, 1.2, ends with 1.6, 1.5. Look at the indexes, 27, 35, 40. You execute this 200 times, the values are not going to change. So the representative sample remains the same. You want to remove this, go ahead. If you don't want to do this, then you see what is happening. Every time the sample will change. You see, some value or the other is always going to change. Now it depends on what you want to do. Do you want a random sample every time? In this case, I want. That is the reason why I'm not going to use that value. But in many cases, we would like to fix that value. Okay, we would like to fix that value so that it doesn't change because of introduction of new data. And that's why in many cases, you will be using random state equal to 1. We will see those cases later on. Okay, don't worry. There are practical reasons why you may want to keep that random value being equal to 1. Okay, but in this case we are not doing it. So I have taken a sample. Okay, I have taken a sample of 10 values. I have total, let's say, 50 values. I have to do t-test. Okay, so let's do t-test. we perform one sample t-test. When you perform one sample t-test, what you do, SciPy is the library you go for. SciPy is implemented as SP. sp.stats. Stats is the module in which I have t-test. Here I have a t-test, which is a variation called one sample, right? It is called one sample. T-test underscore one sample is the function which takes some arguments and it is going to do the one sampling test for us. So what are the arguments? Let's go back once more. Arguments are sample values and mean of population. That's all it needs, right? So what is mean? These are the sample values. So let me just put the sample values first. And then it needs the mean of the population. So how do I get the mean of the population? In this case, I have access to the population, right? In this case, I have access to the population. This is my population. Or to get the mean, what I can simply do is this. Did you get my point? So this is what I can clearly do to get the mean of the population, right? Because in my case, this Setosa data frame itself is the population, out of which 10 random samples changing every time I execute this code, as I've already told you, is going to be my random sampling, right? So I've got both. In many practical cases, you won't get it like this. Okay, I believe Sarangs is raising a hand. Go ahead, Sarangs.
Yeah, Pomik. So while doing, it's a one sample t-test, right?
Yeah.
So I mean, so the two random samples you are comparing,
No.
right? So are you comparing two random samples or a
No.
single random sample?
Single random sample. This is a one sample t-test. So in this case, the first value that I've entered, this is the sample,
Okay,
right?
so you're taking only one random sample, right, out
Right,
of the population.
right,
Okay, okay, okay.
right. The second one is not a sample. You see, I have taken a mean of the population.
Yeah, I
Now,
got it. I got
what
confused.
I'm
I
okay.
thought you were taking multiple samples
No,
into
no, that
data
I'm
frame.
going to do in the two sample test now. After this, I'm going to do that.
Okay, okay.
Right now, this function, if I simply execute this, it will give me two values. Okay, I just want to store those two values into a variable. Okay, the first one I don't need any name, so that's why I am simply giving it as underscore. Underscore is an unnamed variable. You don't want to name that entity, you give it underscore. This is a very unique feature of Python. The second variable that I'm giving over here is the p-val or the p-value. I'm interested into p-value, that's why I'm only keeping p-val as a declared or a specified variable, and I am going to get the value of p. So if I execute this, I get the p-val. Name mean is not defined. Oh, sorry, I have to use np.mean. Fine. So I execute this. I got the mean of the population as second input, first input random sample, and then I got the p-value. So let's do a quick check to see if the p-value is what I want it to be or not. So what I do, call the function, right? I simply pass the p-value. Let's say what it is giving me. We failed to reject the null hypothesis. We failed to reject the null hypothesis. It means the sample represents the population. As simple as that. That is what our question was, right? Our question was, sample is representation of a population or no? As simple. That is null hypothesis. We failed to reject the null hypothesis. That's why the sample is actually a very good representation of the sample. At least by looking at the mean, maybe we can verify. Okay, let's see if that is really the case or not. So np.mean is something like this. This is the mean of the sample. What is the mean of the population? You see, both are quite close. 1.45 is the first one. If you do a round of this and give it value of 2, this comes out to be 1.5. And if you do a round of this and give it a value of 2, this also comes out to be 1.46 or something. So this is quite close. Only by looking at the mean, you can see that the rest of the variables may be very close. The mean is one of the most important features what we see. So as to understand if the mean or the middle part of the normal distribution, if you try to visualize normal distribution in front of you, the middle part of the diagram, if I overlap the diagram or the distribution for sample as well as the population, they should overlap. Okay, the mean should be overlapping. So that's what we are trying to find. Now, if we could have done this clearly, then why do we need all these functions and all those things? Because this function is not only comparing the mean, it is also comparing rest of the values, which you cannot find from here, but it's actually doing those things in the backend. That is a formula that it's to apply. Okay, if you want to know the mathematical formula, you can go to Wikipedia and read. I'm not going to delve into that because it's not going to be fruitful. Does type 1 or type 2 error play a role in the rejection or null hypothesis? Yes, Aransh, it will do. So when we look into type 1 and type 2 errors, we have not started looking into that kind of example. But yes, what Saransh is saying is, does type 1 and type 2 error play a vital role in, let's say, rejection or non-rejection of the null hypothesis? The answer is yes. So at a later point in time, we are going to do that as well. Okay. So let me just comment this. Use the pre-created function to check the status or outcome. All right. So this is one tail test. We have successfully done one tail test. Let's do a two tail test quickly, and then we can conclude. And then maybe later on, we can do some more tests in the next class, right? So now I want to again go back to my first example, the one that we were discussing. Are the distributions of sepal length and petal length for iris comparable with each other? Okay, so this is one of the questions we tried to do, right? But we were not able to do. So let's just take this over here and let's try to define this. Finally, what is going to be the null hypothesis in this case? The means or features of PL and SL are same, right? So the null hypothesis says there is no practical difference between the petal length and the sepal length, which means I can use any one of them to find out what is the species of the flower. They can be a definitive feature to find out the species of the flower. We have already done some visual EDA, hence we know this is not the answer. So we know we are going to reject the null hypothesis already. Okay, but imagine we don't know that, right? Just imagine we don't know that. Just imagine we have two samples and we are going to create two samples now. So one we have the PL and one we have the sepal length. We may want to compare the population as well. That is also something that we can do, but let's start with the sample to sample and then we are going to do a population to population, right? So the null hypothesis, features of PL and SL are the same, statistical feature. Okay, so I'll write stat features. Okay, stat features of PL and SL are the same. Okay, and here it is just the opposite. So it is clearly alternate hypothesis is just the opposite. Okay, SL are not the same at all. Okay, so let's try to test this. Okay, this is my next test. This is where we do a two sample test. Why? One of my samples is PL, the other sample is SL. Okay, one is the petal length, one is the sepal length. Hence, I'm going to do a two sample test. I'm trying to compare two samples here. Okay, so let's try to do a two sample test, right? How am I going to do the two sample test? Is as simple as I'll go back and do a copy paste. Okay, copy and paste over here. We perform a one sample test. Let me remove this line. I don't need this. Everything else remains the same. The function changes and the parameters are going to change. Okay, that's all. That's all is going to change. Nothing more or nothing else. In this case, what I'm going to do, this one, right? This T test one sample, this gets changed to IND. This test is also known as a test of independence. Okay, test of independence is also like comparison of 1 and 2. Right? So what I'm going to do in this case, I'm simply going to define variables A and variables B. I'm simply going to delete this from here and then I'm going to say, you will quickly come to know what is happening here. Okay, so don't worry. So here I'm going to define two variables A and B. Okay, these are the inputs of the parameter of the independent test using t-test. Okay, this is a t independent test or a two sample t-test. The first parameter is the first sample. The second parameter is the second sample. Is my code right? The answer is no. The first sample has to be petal length. The second sample has to be sepal length. So I have to change it over here. The next thing I would like to tell you, this sample function over here is good if I want to really take a sample. Because I have already subsetted data of iris into Setosa, I may want to remove that as well, which doesn't matter, right? So I'll do one test without and one test with. Okay, so in this case, I have done a test with the value. Let's check the p-val condition. Let's see if it is giving anything. We reject the null hypothesis. We already knew the answer, right? Before even starting the question, we knew the answer, right? We knew the answer that we are going to ultimately reject the null hypothesis. The properties of the Setosa flower's petal length does not match with that of the sepal length. We already know that because we have done some visual analysis earlier. What happens if I want to do two sample tests, although we don't have much time? Let's just quickly test this and then we can make it a call. We can make it a close if we can quickly test this. Now I'm not interested in a sample. I'm not interested in any one species. Let me get rid of all these things. And I would like to compare two populations. I'm taking the entire data frame. That's why I am comparing two populations. So let's see what is the case. In this case also, we reject the null hypothesis. Now I'm able to compare the population because I have access to the data of a population. Had it been the case I have no access, I couldn't have done that. Okay, let's make it a call here. I believe we are running out of time. I'll share the code. Please have a look. Let's continue tomorrow. Thank you.
Thanks. Thank you.
Thank you. Thank you. Thank you.